Hey, hi everyone, my name is Hardik, and in this video and in the following videos I will be going through the exercise 1.b of the book Linear Algebra Done Right. And I'm currently going through this book, and while I'm solving the questions, I'm also documenting them through these videos for myself because it helps me to understand more when I try to explain, and also it will be much better for me if anyone else also find it useful. Alright, then we'll start with the first question. The first question is, prove that minus of minus v equal to v for every v belonging to capital V. So I will write it. So we have to prove that minus of minus v is equals to v for every v belonging to the vector space V. Now V is the vector space. It is not mentioned in the question, but it has been mentioned earlier in the section in the book that whenever we mention the capital V, it will represent a vector space. And as you might have gone through, that a vector space is a set which follows the given 10 conditions, and also a vector space has some properties which are given in the book. Now it must seem like very obvious thing that isn't it minus of minus x. So why do we have to prove this? Well, because this doesn't work like that. Like, we have to use only the properties of a vector space, because when we talk about vector space, it is a set which is defined and so a vector space, basically we are also passing the plus operator and the multiplicative operator. So this can literally be anything and this can be anything. So it's not necessary that the plus is the normal algebraic plus addition that we see and this is multiplication. It can literally be anything. So we only have to use the properties of the vector space to prove all these questions. So how do we prove this? Well, we'll take the equation or the theorem 1.31, which is like above the exercises, and it says that v plus it says that minus 1 of v is equal to minus of v for every v belonging to that vector space. So this is given. So now what we can do is, since we know that minus v also belongs to the vector space, because like again this is a property, so if v belongs to a vector space v, then alpha v also belongs to that vector space v, where alpha can be any scalar, and this time it is v, and also minus v is the v inverse. So these are all the properties. I'm just repeating the properties. Alright, so then since this also belongs to the vector space, so this condition also holds true for minus v, right? So we can just replace v by minus v and this property will still be holding. So let's do it. So minus 1 times minus v is equals to minus of minus v. So let's say this equation was equation number 1 and this is equation number 2. And now just replace the value of minus v from here to here. So what will we get? Minus 1. So minus v is minus 1 times v is equals to minus of minus v. Now minus 1, because it is associative, so we can multiply them together, and minus 1 and minus 1 both are real numbers. So minus 1 times minus 1 times v equals to minus of minus v. And what is minus 1 times minus 1? Because they are both real numbers, it will be plus 1. So plus 1 times v equals to minus of minus v. Now this is also the multiplicative identity, so this will be v only, so v equals to minus of minus v, and hence we have proved. So in every step we have used some or the other property of a vector space, so please keep this thing in mind. This will be useful in the upcoming questions. Second question is, and I will wait 1 second. Yes. So now we come to the second question, which says that suppose alpha belongs to field F, there's V which belongs to the vector space capital V, and a condition is given that alpha times V is 0, and we have to prove that either alpha is 0 or V is 0. So prove that alpha is 0 or V is 0. I mean, man, it sounds so obvious, right? Alpha times V is 0, so one of them has to be 0. But we have to prove this given the conditions of a vector space. So this is our constraint, we have to prove it using that, and even if it is like very obvious. So we start with the opposite. So we say that okay, alpha V is 0, we accept it, and let's suppose that alpha and V, they are both non-zero, and this condition holds, right? So if we contradict it, then our what we have to prove will be proved. So how do I contradict it? So I have to prove opposite of this. So I have to prove either that alpha is 0 or V is 0. Now how do I do that? So this, okay, so what is alpha? Alpha belongs to the field F. So it is a real number. And what is V? V is an element of the vector space capital V. So all the properties of vector space is followed by V. And then we have 0, which is a number 0. So this is also a real number. So, okay, now how do I start with? Well, I can eliminate this alpha by multiplying it with its multiplicative inverse. So let us say it was alpha inverse times alpha V is equals to alpha inverse 0. Now this is a real number, this is a real number, and these two are real number also. These are multiplicative inverse of each other, so this will give us 1. 1 times V is alpha inverse 0, again would be 0. Now 1 is the additive identity, and additive identity times something is something, so this is a property of a vector space. So V equals to 0, and this V equal to 0 is a contradiction to our initial conditions. So by contradiction we have proved that if this is 0, then V has to be 0. Okay. So the next question is that given V and W, which are elements of a vector space, we have to prove that there exists a unique X which is also belonging to the same vector space, such that this condition satisfies. Now again, give a moment and go through the question and try to understand like what it is about. So we have to prove that this X is unique, and there exists an X and this is also unique. So how do we prove it? How should I approach proving this? Well, again, just as we did the last time, we will start with the opposite of what has to be proved, and by contradiction we will prove that the original condition is true. So what would be the opposite condition of this? Well, we have to prove that there exists a unique x. So let's start with that that the x is not unique, or there are two different x which is satisfying the same condition. So let us say x1 and x2 belonging to V such that x1 is not equal to x2, x1 is not equal to x2, and this condition holds. So V plus 3x1 is equals to W, and V plus 3x2 is also equal to W. So there is not a unique x, but there are two different x which is satisfying the same condition. And now to solve this, let's say this is equation 1 and 2. We have to disprove this thing here, that the x and x2 are not unique, but they are the same, and same means like it is a unique. So how do I do this? Well, this is one equation, this is the second equation. Let's subtract 2 from 1. So what will we have? We have x plus 3x1 minus V plus 3x1 minus V plus 3x2 equals to W minus W. Right, so this W minus W is, we can see, because they belong to a vector space, and this W is the additive inverse. So we are adding the additive inverse, and whenever we do that, it's always 0. This is a property of a vector space. And on the left hand side we have V plus 3x1. Now because it is distributive also, so it will distribute inside, minus V minus 3x2 equals to 0. We can club them together. We have V minus V plus 3x1 minus 3x2 equals to 0, and again it's an element of a vector space, and we are adding its inverse, additive inverse, so this will also be 0. So we will left with 3x1 minus 3x2 equals to 0. Now again, because it is distributive, so this term again, so this term is 0. So now this one, because it is distributive, it's 3x1 minus x2 equals to 0. Now this is a real number, and this is the element of a vector space, and we have seen in the last one that if alpha times V is 0, then alpha is 0 or V is 0. Now obviously alpha is 3, so it's not 0, so this condition x1 minus x2 has to be 0. So now we just, we can add the additive inverse of x2 here, which will give us x1 minus x2 plus x2, because additive inverse is minus of minus, and here also it will be x2, so again these are additive inverses, cancel out, plus, so this will be x1 left here and x2 here. So we prove that x1 equals to x2, which is opposite to what we started with. We said that x1 is not equal to x2. So hence by contradiction we say that this is not correct, and x1 and x2 are same, and x, so let's say this is x, so there is a unique x which satisfies this condition. So coming to the fourth question, and this is a bit more theoretical as compared to the three that we have done earlier. So the question is that empty set is not a vector space. The empty set fails to satisfy only one of the requirements listed in 1.19. Which one? So empty set, again, so if we have to prove that a given set is a vector space, we have to show that that set follows the 10 properties. Now what are those 10 properties? So the first one is that the addition and the scalar multiplication are closed, which means that given there are two elements in the set, so when we add them, the addition also belongs to that that set. And then secondly, if we have a scalar and any element from that set and we multiply them, then the product has to belong to that set. Now if these two properties are satisfied, which is, so if this is satisfied, it is said that that it is closed under addition and it is closed under multiplication. Now the next conditions are commutativity, associativity, additive identity, additive inverse, multiplicative identity, and distributive properties. So now which one of this is not satisfied by an empty set? So we have an empty set, so it is basically nothing. So which one is not satisfied? Now let's start with the first one, addition. So it is said that given u plus v belonging to the set, given two elements belonging to the set, but this one doesn't have any elements, so this is not like it is not neglecting this, or what is the right word? Disprove? Yeah, it is not disproving it. Similarly this one, because there is no element, so this condition is not false. Similarly commutativity, because there are no element in it, so this condition is not false. Associativity also, because it is said, and how I think is, it said that u plus v is equals to v plus u for all u v belonging to v. Now this is not true. I mean, there is no u v that belongs to v, so we are not even going here, we're not even checking this. Here only this condition is being like satisfied. And similarly for associativity, so can you guess which one would it be? Well, the answer is additive identity. It says that there should exist an element in that set 0 which follows this property, and this is the only condition which like in which there has to be an element beforehand, even before checking the condition. So this condition is not satisfied by an empty set because there is no 0 element. So this condition, it fails to satisfy. Now moving on to the fifth question. So it's saying that show that in the definition of a vector space, the additive inverse condition can be replaced with the condition that 0 times v equals to 0 for all v belonging to the vector space v. Here the 0 on the left side is the number 0 and 0 on the right side is the additive identity of v. a little confusing, right? So this is, as mentioned in the question, this is the number 0 and this is the additive identity, but it's like written in the same symbols. So anyways, so what is the question? So the question is that the condition for additive inverse, and what is that condition? That is that v plus the additive inverse of v is 0. 0 here is the additive identity for all v belonging to capital V. Why do I write x? It's v. So if I've written this in earlier videos, please ignore. It has to be v. I'm obsessed with my... Oh, okay, leave it. So this condition here is the additive inverse, and we have to show that proving this is equivalent to proving this. Now let's see how we can do it. So we have V plus V inverse is equals to the additive identity. Let's call it 0 only. So now V plus, we can write V inverse as -1 of V, right? So this is 1.31. Now we can also write V as 1 times V. Why? Because it is the additive identity. Yeah, okay, so we can write it this because this is the multiplicative identity one. And now we can use the distributive law. We can take V out and we can write this as 1 plus -1 double brackets equals to 0. Now again -1, this is a real number only, so we can write it as 1 minus 1 times V equals to 0. And what is 1 minus 1? It is 0, the number and this is 0, the additive identity. And right, so this is what we had to prove. So proving this is equivalent to proving this. So we can replace this condition in the 10 laws or the 10 axioms or the conditions to prove that a set is a vector space. Out of that, this one can be replaced with this one. So this is what we had to prove. So it's the last question of this exercise, and in this we are given a set R union an object infinity and another object minus infinity, and we are also given the rules, how they are added, how they are multiplied, and we are asked that is this given set, is this a vector space over R? Now if we have to prove for any set to be a vector space, we have to prove that it holds the 10 properties or the 10 conditions, and if any one of them is false, then it is not a vector space. So this is a task for you to go through all the 10 conditions and check one by one which is true and which is not. And because I'm very late in night and I have to sleep, so I will just give you the answer on why is it not a vector space. So let's take any t. So here t belongs to this R. So if I take elements t plus infinity minus infinity, so what it would be? So t plus infinity is infinity. Then we would have infinity minus infinity. So this would be 0, right? Infinity, yeah. So it is actually infinity plus minus infinity is an object, so we'll treat it like that only. So infinity plus minus infinity, that would be 0. But if I take some different bracket here, so let's say okay, let's say t plus infinity plus minus infinity. So what this would be? So infinity plus minus infinity is what? 0, and then t plus 0 is t. So we saw that t plus infinity plus minus infinity is not equal to t plus infinity plus minus infinity. So this is not associative, and if it is not associative, it cannot be a vector space. So thank you. I hope this video was of any help to you. Bye. Take care.